Okay, let's look at this example 7.2 again, but this time let's be a little, let's use some of the kind of lessons learned, if you will, that we've gained from this. One of the things that we've learned is that the shear is constant value between concentrated loads, right? And we showed that. So here, let's come in here. I'm gonna just extend these lines down to here, just to make life a little bit easier. So here's my, this is gonna be my V, my shear, and here's my bending moment. Okay, and then just as some points of reference, there, and there. Okay, and we've learned from the when we did this before, we learned that this is 46 and this is 14. Gonna draw that down here where we can see it nice and clearly. Okay, so that's just gratuitously using what we've learned before. So now, again, what we learned is if we cut it off right here, that shear, remember the shear is going to be in that direction. The shear starts at minus 20, and if we cut it here, it's still going to be only one force. It's going to stay minus 20. So this is going to stay minus 20 all the way up to this point right here. And then if we cut it here, again, just as a little gut check, we have 20 coming down. Now we have 46 coming up. I'm going to erase that and draw just so if we do a V and a M here, that V, so up until that point, I lied, I'm going to come in here. So no matter how far, I'm going to have a V here. This is always going to be minus 20 because there's nothing until we get to the point where now I have this and I have 46 coming up, 20 going down. So now that V has to switch from minus 20 to being positive 26, right? So it's going to come up here, boom, to 26. And it's going to maintain that all the way from here over to here. So that's going to be positive 26. This is 26. And then here, this is equal to 26, so that works out. And then you end up with this thing 20, 46, and then eventually we have 40 coming down here. So now when you have V is going to have to equal to what, minus 14. So 20 minus 14. So this is going to have to drop down to minus 14, and then it's going to stay constant to here and go back to there. So that is, for concentrated loads, life is actually nice and, quite frankly, nice and easy. You go through and it's just it's just nice constant values. But then what we just learned is that the moment is dependent on the area of this. Okay, so what is the moment there? The moment starts at 0 because we went through, and if you take the moment, so actually let's go back here. If you have a force, well, if we have a force here and it's cut right there, we have the V and M. There's no lever arm, so moment starts at 0. But what we're saying is that the area of this curve right here is how much the moment changes. So what is that area? It's 20 times, and for what it's worth, it's a negative 20, right? Times 2.5. So it's minus 50. So it changes by 50. So from here to here, you end up with at minus 50. So it changes nice and linearly, by 50. And then what's the area of this curve? Well, the area of this curve is 26 times 3. So what is that? 78, I believe. 26. Okay. So it changes. So the moment, the delta moment, is plus 78. So it goes 78 from here to here. So 50. So minus 50 plus 78 is equal to positive 28. So it goes from minus 50 up to this here, which is 28. So it changes by 28. And what is this curve right here? Well, this is minus 14 times 2, which is equal to minus 28. So the change is minus 28. And since I'm starting at 28, it goes back down to 0. So that ends up being that. So if you just watched the video on the other one, what was it, 20 minutes to do all that? And now we just knocked it out in like 5 minutes. So this is definitely the easier way to go. That you can, the bending moment, knowing that the bending moment is related to the area of the shear moment curve, and with concentrated loads, it's the shear stays constant between the loads, so therefore you can figure out the bending moment. So this is actually a much easier, less painful way to get to the same answer.